Good morning, everybody. Thank you for being here. I hope I'm already getting excited by the talks which have been given and looking forward to the talks which are going to come. So my talk is about understanding the high energy ultraviolet and X-ray emission from AGB stars and what they imply in terms of episodic accretion in binary systems. My collaborators on these are Jorge Sanz-Forcada, Martín Guerrero, Roberto Ortiz, and Carmen Sánchez Contreras. Well, Albert already mentioned this in his introduction, but let me just show you a more picturesque version of the kind of morphologies which you see in planetary nebulae. This is a small mosaic of a large survey that we did with the Hubble Space Telescope. And these, I've chosen multipolar objects because these are perhaps the strongest indicators that there's something coming out from the center which can change its direction, specifically fast collimated outflows, which become operational at the late AGB or early post-AGB phase, which then carve out these beautiful morphologies in these objects. 50%, greater than 50% of young planetary nebulae have extreme aspherical morphologies, and bipolar and multipolar symmetry is quite common. So the consensus now, at least within the community, is that binarity is probably the most probable cause of producing these outflows, which then cause the shaping, and they must be operating during the late AGB or the early preplanetary nebula phase. So of course, then the question arises, is there evidence of binarity in associated accretion activity in AGB stars? How can we find such evidence? So, as I said already, binarity is likely the underlying cause, and there's of course a lot of theoretical work which has gone on, which shows what binarity can do for us in this scenario. I mean, you can have common envelope ejection, you can have accretion, which then results in the formation of jets, you can have torus formation, you can enhance the rotation of the AGB star, you can produce magnetic fields, etc. And all of these can help us produce the kind of shapes that we're seeing. Some of the fundamental questions that we want to know, I'm not going to address all of them in my talk, of course, but I just want to bring them to your attention, are you want to understand what the origin, the properties of the shaping agents are, these collimated fast outflows, which appear to be operating at few times 100 kilometers per second. What are the origins and the properties of the equatorially dense structures, which are seen in many of these objects? What is specifically the role of the magnetic fields? And an interesting thing, an additional interesting question is, why are there two observational subclasses of post-AGB objects? That is the preplanetary nebulae, which have morphologies very much like planetary nebulae, and the disprominent post-AGB objects, where the central stars are known in most of them to be radial velocity binaries. They have disks, but they have very little extended structure. And the disks appear to be where you can measure the rotation, appear to be rotating. So, looking for binarity. Well, early on when the GALEX satellite went up, the observatory, which operates in ultraviolet, we realized that we could actually look for the binary companion in the ultraviolet, because even though the cool primary, even though primary is 10 to the 4 solar luminosities, it is cool. And if your companion, even with the solar type luminosity, is 6,000 Kelvin or higher, then you can actually detect it in the ultraviolet. So we did this experiment, and lo and behold, we actually found that many of these objects that we looked at had far ultraviolet and near ultraviolet excesses. And this plot just shows a fit to the data of the AGB star, and you can see the blue curves show the AGB star fit, and the data, and the green curves show the companion which has been fitted to the ultraviolet points. Now, though we fitted a companion, we found that the companion, if it's a main sequence companion, the luminosity and the temperature do not follow the main sequence. So, and we noticed that the FUV and the NUV fluxes are variable. So we realized that most likely we're not seeing the companion directly, we're seeing emission in the ultraviolet resulting from accretion activity associated with the companion. So we did a survey of all the objects of AGB stars available either because of direct observations, because of they were just part of the all-sky survey, to look at the variability of the ultraviolet. And we found that, yes, lo and behold, both the far ultraviolet and near ultraviolet, GALEX has two bands, far ultraviolet and near ultraviolet, is very, very variable. And of course, if there's a companion associated, as we think, related to this activity, then these variations could be explained as variations in the emission measure or the obscuring column in front of the ultraviolet, and the periods with where the far ultraviolet and the near ultraviolet variations are anti-correlated. Those could be a result of variations in the temperature of the plasma, which is producing the ultraviolet. So again, the indications from this variability are that this is associated with accretion activity associated with a binary companion. Now, can we show, so then the question was, can we try and show this directly, at least for some objects? So we chose the brightest object in the far ultraviolet from a sample of AGB stars. And we did a spectroscopic survey of that with the Hubble Space Telescope to look at, can we actually see signs of infall, outflow, et cetera, which would be associated with accretion activity. And lo and behold, yes, we did. Here on these plots actually show, well, on the left-hand side, the panels from the top to the bottom show variations first in the continuum. And you can see the continuum is varying up and down on time scales of 20 seconds or less. The emission line fluxes are varying, and the velocity is also varying. So everything is highly variable. It's a very dynamic environment. And the right-hand side, on the bottom two plots, you see how the luminosity is varying, which has been estimated from black body fits to the continuum. And so what we can say from this, or we can infer, is that these variations are most likely associated with the accretion flow. The flickering, which is of order of 20 seconds or less, is associated with an accretion disk. Accretion disks traditionally produce flickering. The emitting region has to be less than about 1/10 of an AU and could probably be the size of an accretion hotspot. And the mass accretion rate is a few times 10⁻⁷ solar masses per year. And the bottom, you see a little cartoon of what we think that this object really looks like, with a big, humongous primary and a companion with an accretion disk, which has been produced as a result of accretion of matter from the primary outflow and produces a fast collimated outflow. And you see both the fast collimated outflow in the spectra, and you see infalling gas in the spectra. So this is a very nice confirmation of this model that we have. So how do I go to the next slide? Okay, so now I switch over to, so this is what we've done in the ultraviolet. Now let's look at what can we do with X-ray studies. So when we thought, or when we came to the conclusion that most likely we have accretion activity related to a binary companion, we said, hey, let's look at these things in X-rays, because if you have very hot plasma, you should expect to see that in X-rays as well. And so a number of people, including our group, did look at X-ray observations, both with XMM and with Chandra. And we chose a small sample of objects with fairly high FUV to NUV ratios, so as to maximize the chances of seeing X-ray emission. And lo and behold, we saw X-ray emission in about 40% of these objects. And again, the plots on the top show you the fluctuations, the light cycles in the ultraviolet and X-rays. And again, you see fairly quick, fast variations, again, which is probably a result of flickering. With the Chandra Observatory, for Y Geminorum, you see a plot of, again, the light curve, and there seems to be some periodicity associated with that as well. And so that's likely associated with the binary companion itself in a very, very tight orbit around the primary companion, around the primary star. The hardness ratio we can estimate for some of these objects also varies with time, and again, most likely due to variations in the obscuring neutral column density in front of the hot plasma, which is emitting in X-rays. So now so these are small samples which we have looked at in the X-ray. So now let's try to understand what are the far ultraviolet and near ultraviolet properties of all the AGB stars which we can detect in the ultraviolet as a whole. So we find the dominant fraction of UV emitting AGB stars are in fact not those stars which have far ultraviolet as well. In fact, most of the stars which are seen in the UV only have near ultraviolet. or if they do have far ultraviolet, the ratios of the far ultraviolet to the near ultraviolet are relatively low, less than about 0.1. And in a paper, it was suggested that maybe this has nothing to do with binarity. Maybe it is just chromospheric emission from the primary star. So to examine this, to investigate this question, we looked at an input catalog of 3,500 AGB stars in the galaxy and looked at the properties in the ultraviolet. We found that 20% of them were detected in one or both of the far ultraviolet and UV bands, and about 10% were detected in both these bands. Now, the above fractions are likely to be lower limits because the exposure times are very short, because these are all observations taken in the all-sky survey. So these two plots show you a plot of the far ultraviolet versus near ultraviolet of all the objects that we detected in these two bands, and a linear fit to it. And the linear fit has a slope of 0.06. So that tells us that the typical ultraviolet emitting AGB star has this ratio. Now, skipped too many slides, I think. Sorry, it's not doing what I wanted to do. Okay, yes. So in order to understand whether we could explain these objects, the bulk of the population of ultraviolet emitting stars is chromospheric emission. We made a grid of about 50,000 cloudy models, which is sort of a mock chromosphere. So it's a primary star, AGB star, surrounded by a thin layer of fairly hot gas, and with a range of densities, with a range of temperatures, etc. And we plotted and from these models, we computed the far ultraviolet near ultraviolet ratio, and we plotted that as a function of the far ultraviolet to the K-band flux of these objects. So this plot shows you the purple crosses are the data, the green crosses are, the green symbols are chromospheric models with temperatures in the 9,000 to 11,000 Kelvin range, which is the typical for chromospheres. And the blue symbols are elevated chromospheric temperatures. Just assume that maybe chromospheres can be that hot, but typically that's too high for a chromosphere. And you can see that the green symbols fit far ultraviolet to near ultraviolet ratios up to about 0.06, 0.07 or so. If you elevate the temperature a little bit, you can go up, you can probably fit a far ultraviolet to near ultraviolet ratio about 0.1. But you can see there are a lot of AGB stars which are above that ratio. And most likely, we conclude that those stars cannot be fit by chromospheric emission. Now, of course, this chromosphere can be around the primary star, or it can be around the companion as well. So the fact that you can fit it with a chromospheric emission does not necessarily rule out the fact that there's a companion present. And in fact, we said, well, let's look at, we've been focusing so far on objects which have high FUV to NUV ratios. Let's look at the objects with low FUV to NUV ratios, which are supposedly the objects which can be explained by chromospheric emission. So we put in in AO19 or XMM, we put in a small survey of 7 what we call NUV AGB stars, that is stars with low ratios, less than 0.08. And only 2 objects have been observed so far in this. So so TW HOR and EPS OCT. So we find that TW HOR, for which I show you the plot here, was actually detected in X-rays, even though the ratio is 0.04, which is small. And in fact, we can fit it with the best fit. You can fit with a 1 component or 2 temperature component model. The 2 temperature component model gives you a slightly better fit. But the dominant component is a low temperature component, about 10 million kelvins. And so with a luminosity about 10 to the 30 ergs per second. And so we think that this is most likely coronal emission from main sequence companion. So this tells us that even the objects which presumably could be explained by chromospheric emission may also have companions. And we certainly need a more extensive X-ray study of such objects. Hopefully some more of the objects in the study which we have proposed, which was proposed and was accepted, will be observed. So we'll know a little more. Interestingly, the second object, which is EPS OCT, which has a higher ratio, was in fact not detected. And that object is actually significantly closer to us than TW-HOR. So there's a, we can set a fairly sensitive upper limit on the X-ray luminosity, and yet it's not detected. So something very interesting is going on. Our current hypothesis is that a very large fraction of these UV emitting AGB stars do have companions, and the accretion is variable. And when the accretion activity is low, you typically pick up the coronal emission from the main sequence companion, as you're doing in the case of TW-HOR. And when the accretion activity is high, then we pick up the objects which I showed before, which was from my list of from our studies with the AGB stars with the high FUV to NUV ratios. So with that, I'm going to close here. Just put up my conclusions here. So a significant fraction of the galactic AGB star population shows UV emission. The UV emission is variable, indicator of variable accretion activity, presumably due to binary companion, and is supported by detailed spectroscopic study of one object. Of course, we would like to have similar studies for more objects if Hubble will give us time to do that. For stars with this ratio of FUV to NUV of 0.1, accretion activity or higher, accretion activity is a likely mechanism and is supported by X-ray studies. For stars with a lower ratio, a chromosphere can produce the observed UV emission, but some fraction of these likely also to have companions. So the chromosphere, the emission is probably from the corona around the companion. So I will stop there and open it up for questions.
I have to click several times to get myself to unmute. Yeah, there are a few questions already. We're running a bit over time, so I'll have to make some selection. Xu Chen has asked a question in the chat on how do you estimate the accretion rate?
Well, the accretion rate, so there's a formula, I think, presumably given by Mario Livio and colleagues, where the accretion rate is GMM M primary M companion divided by the radius of the companion, and that has to be greater than I mean, so you have the accretion luminosity. You estimate the accretion luminosity. The accretion luminosity has to be less than that accretion rate, and so from that we can estimate a lower limit of the accretion rate.
Okay.
So basically, we measure the accretion luminosity, and then from that we calculate the accretion rate.
Good. It did occur to me that your accretion rates were similar to the mass loss rates you might expect from the star.
Yes.
Adam, you had a question.
Yeah, I think actually it's been answered, but let me just ask. You seem to get evidence for both inflow and outflow. So if you can get accretion rates, can you get outflow rates from the disk? You're assuming this is onto the companion, because like that's the jet. Right?
Yeah. Yes, we can if we have a little quantitative model of the outflow, which we did not make in that paper, but we're working on that. So we can then get an outflow rate and see whether the outflow rate is, a tenth of the accretion rate, which is the canonical expectation for outflow when it is powered by accretion.
It's very exciting. It's very exciting to actually be able to see this now. This is the end.
We would very much like to do this for at least a few more stars, but Hubble has not decided to give us time as yet for a more extensive study.
Ursula, you had a question?
Very quick. Hi, Raghvendra. Are there any ALMA pictures of your sample? Because you could correlate what's going on using one of the super high resolution envelope of AGB ALMA images.
I don't think that we have very high resolution images of any of these objects. That is something which I would very much like to do. And I've been thinking about that, putting a proposal to study some of these objects in detail with ALMA and look at the structure very close to the central star with very high resolution. These objects don't tend to be very high mass loss rate objects, which is expected because their mass loss rate is very high, then that will extinguish the X-rays and the ultraviolet, and you probably won't see them even if they're emitting in those at those wavelengths.
Okay, thanks. Raghvendra, if you could stop sharing your screen.
Right.
Yeah, then we'll move on